now we move to higher dimensions elastostatics. And so we are going to have something very similar to what we just did, with some subtleties, because we're no longer going to be dealing with a scalar field, but we have vector fields. Okay, so
Are you recording?
yes, elastostatics in higher dimensions. Okay, remember what we did a few minutes ago. We're going to do the same. We're going to have our mechanics potato. We call that omega. We're going to have some part of our boundary with prescribed Newman boundary conditions. We're going to call that T prescribed, so it's a vector field, right? We have our normal vector field to the boundary, always outwards. We're going to have one portion of our domain with prescribed Dirichlet boundary conditions. We call that gamma u. And again, we're going to have some part of the boundary that is connected with some sort of spring to Earth. We call that part of the boundary gamma h, and that is where we're prescribing our Robin boundary condition. So again, given some quantities, and what are those quantities? Well, we have the body force, B, right, which is actually omega, but now we are dealing with a vector field, so this is in RD. D is the dimensionality of the problem, so that is going to be 2 in 2D, 3 in 3D. This is the body force. We have our prescribed displacement, which is a vector field. We have our prescribed traction, gamma t. And now we're going to have this h, which is now a tensor. And because it is a tensor, it goes from gamma h to RD cross RD. And we're going to say that this is our elastic support, the same way we have done it. Remember that as we usually do, we define the boundary, right, our omega, which is basically equal to, well, our gamma is equal to our d omega, right? We define that as the closure minus the open set. And we also have to say that, of course, that is going to be equal to gamma u union gamma t union gamma h, the closure of that. And we also say that these regions are mutually exclusive, so this whole thing here is equal to the empty set. Okay, so now that we have all those, we are ready to state the strong form of the boundary value problem. And so the divergence of the stress tensor plus the body force is equal to 0, but it's a 0 vector, so now we are dealing with 2 or 3 equations depending on the dimensionality. Yeah?
Why is the h here d by d dimensional? Because
It's a tensor.
it's a tensor, right? But
Yeah.
like, can the spring also have shear?
Yeah, you can think of some sort of different components or different stiffness depending on the direction. So we make it a tensor.
Okay.
Doesn't have to be like that, but yeah, we could make it like this.
Okay.
So that is going to be in omega, right, inside the domain. And then we have our usual boundary conditions. U is equal to u bar on gamma u. We have now Cauchy's relation between the stresses and the tractions along the boundary. This is called Cauchy equation, and it's basically setting our Newman boundary condition. And our Robin boundary condition, u minus u on gamma h. Remember, as usual, it consists of a part that we know and a part that we don't know. Otherwise, we don't make it. Tell me quickly. Yeah, okay. All right. Now remember, we are dealing, so the divergence, this is what we called the divergence operator. Okay, so sigma is the Cauchy stress tensor. You should all be by now familiar with this. And we're going to be in linearized kinematics, and that basically means that we're going to neglect high order terms in the strain, and our linearized stress tensor can be written as the symmetric gradient of u, which is 1/2 of grad u plus grad u transpose. So the high order term drops, and of course, we're going to assume linear relationship between stresses and strains, and so this is basically the generalized Hooke's law, where we have some sort of C that is linear. This is a linear relationship. Okay, as we normally do, we take this expression here, right? And now, of course, I'm dealing with the weak form. We're going to take that expression. We're going to weight it with some test function that now is a vector field, right? And we're going to integrate that over my domain. And I'm going to set that equal to 0 for all vector valued test functions. So now this W is a vector, and so each component of that vector is going to be a function. That's why I say vector valued functions, right? That belongs to some sort of V naught. Remember that we use a naught just to signify that those functions are going to be, or each component is going to be 0 in the Dirichlet part of the boundary. So how do we define that? Well, my V naught now is going to be defined as the set of vector valued functions V, such that, of course, we're dealing with a vector. So this is in RD. RD is basically a vector for all x, every position vector in omega, such that each component of this vector belongs to the space of functions that we call the Sobolev space. Remember Sobolev spaces? And we're going to deal with H1. That means that the functions themselves, so if you take this vector, say we're dealing with 3 dimensions, we have 3 components. Each component of that vector is going to be a function, and each one of these functions is going to belong to the Sobolev space H1. That means that the function itself is square integrable and has also first derivatives that are square integrable as well. And finally, since it is not, well, we are going to make sure that the restriction of that function to gamma u is going to be equal to 0. Okay? Now, notice something interesting. If we're looking again how we define the weak formulation, the weighted residual, right? Well, B is a vector, sigma is a tensor, so the divergence of a tensor is a vector, so the whole thing is a vector, and so I have to do the dot product now with the test function, which is also a vector, to get a scalar, and that's why I put 0 scalar on the side, okay? Okay, well, now I'm going to use again an identity, and we're going to go beyond that, just writing it. So the identity is simply W dotted with the divergence of sigma, because again, we want to deal with this term, right? Notice that sigma is a function of the strain, and the strain has derivatives, right? And the moment I apply then the divergence of that, I am applying a second derivative. And as usual, we want to relax that requirement. We want to balance derivatives. And so the identity that we're going to use, this is sigma plus grad W contracted with sigma, and that I will explain what that exactly means in a second, is equal to the divergence of sigma transpose operating on W. So that is the identity. And so, well, let's just see what we get. I don't know if you recall from other courses, but, well, if you have 2 tensors, right? Say you have 2 tensors A and B. Well, the contraction between those 2 tensors is basically a scalar that is defined as Aij, Bij, right? So this whole thing here is basically scalar, right? Because W is a vector. The moment I take the gradient where it's a tensor, so that tensor is contracted with another tensor. So this operation is very simple. So you go to the 1, 1 component of the first tensor, you multiply by the 1, 1 component of the second tensor, plus 1, 2, 2, 1, 2, 2, and that is basically a scalar. Okay, well, let's try to very briefly look at that identity. So let's take a look at that term here, right? So sigma transpose. If you recall, the balance of angular momentum tells you that your stress tensor is symmetric, okay? So sigma is actually equal to sigma transpose, but I'm not going to use that property, at least not yet, right? Because I don't need it, right? Just to keep this in mind for the time being. Okay, so let's take a look at that first term. So you have sigma transpose dotted with W. Well, by definition, this sigma transpose is sigma ij, ej tensor ei, because of course it is transpose, and W is wk ek, right? So now this operation, you have a tensor operating on a vector, so that is basically going to lead to the Kronecker delta ik. So I have sigma ij wk delta ik ej, and this thing here is basically going to contract one of the indices, and so that whole thing is going to be equal to sigma ij wi ej. So you see now that we have a vector, right? Okay, well, now we are going to take the gradient of that vector, right? And the gradient of that vector, by definition, so the divergence of that vector, by definition, is basically taking the component of that, applying the derivative to the component of that. So the component is, of course, everything here, is going to be the derivative with respect to xj, because this is the jth component, right? Sigma ij wi. And so, well, we can apply basically that is equal to the derivative of the first term, multiply by the second term as is, plus sigma ij, and then the derivative of this with respect to xj. So this whole thing here is basically our divergence of sigma. This guy here is sigma, and this here is my grad W. Okay, and so everything is going to be equal to that guy dotted with W plus this guy contracted with grad W. Okay, in the book you also have that little explanation. But now that we have that identity, all we need to do is exactly the same thing we did earlier. So we're going to replace that term for this whole thing. And then, of course, notice that now this term is balancing the derivatives, because now we are applying first order derivatives on the W, on each component of W. And then sigma also has derivatives on U that are coming, because sigma is a function of strain, and a strain has first order derivatives on U. And that is how we balance derivatives in this case. Okay? And we're doing well with time. Okay, so going back to the main expression, we have integral over omega W dotted with the divergence of sigma is equal to the divergence of this whole thing operating on W minus this whole thing here. And so because this term is negative, right, the moment we send it to the other side of the equation, right, it's going to change signs. And so now we're going to have is equal to, this term as usual does not change, so it's basically the dot product between the test function and our body force. And then we're going to have, as we happened to had a few minutes ago in the heat conduction, we have that term that involves the divergence of some quantity, right? And that quantity is sigma transpose operating on W. And if you remember, we said, well, we're going to use some sort of generalization of integration by parts. This is the divergence theorem, and we're going to transform that integral over the volume into the integral over the boundary, right? And so we take whatever we have, we're taking the divergence on, and multiply by the normal to make that transformation, right? And so we take, again, we say, well, let's call that 1, and then we are going to say that this guy here is going to be equal to an integral over the boundary, and basically we take everything that we're taking the divergence on, and we multiply that by the normal. Yeah? And by definition of the transpose of a tensor, I don't know if you know this, but if you have some vectors u, and then you have some tensor t that is operating on other vector v, right? That is equal by the definition of the transpose of a tensor as v dotted with t transpose operating on u. That is the way the transpose of a tensor is defined to make this operation work, right? So by definition of the transpose of a tensor, I can write that expression, right, omega, and now I can bring, notice I can basically swap these two vectors, and of course take the transpose of the stress tensor. That's why I said earlier, I know that by the balance of angular momentum, my stress tensor is symmetric, but I'm not going to use that property because I don't need it, right? Because the moment I use the definition of the transpose of a tensor, now basically I get this expression here. So I have sigma dotted with n. And what is sigma dotted with n? The traction. That's Cauchy's relation, right? So this whole thing can be written, again, since we have 3 parts of the boundary, it can be written as 3 integrals, right? We have an integral over gamma u, where my w is going to be multiplied by what?
By t.
By t where?
Well, in 3 dimensions, right?
So how would we call this part of the boundary, the traction on the part of the boundary where we're prescribing directly boundary conditions? We call it R, which is the reaction force. Thank you, sir. Okay, plus we have a part gamma t where W is dotted with the traction. This is our prescribed Newman boundary condition. And we have finally the part of the Robin boundary condition when this is gamma h, and now we have W dotted with this whole thing. Okay? Obviously, remember that the way we have defined the space, each component, so each vectors that we're going to choose, again, are going to be 0 in that part of the directly boundary condition, the same way we have been doing it from the beginning of this course, right? And basically that means that this term here is what? That drops. Going to be equal to 0 simply because W evaluated at gamma u is equal to 0. Okay? All right. One more thing here is that we have this expression here. And now for the first time, I'm going to use the fact that my stress tensor is symmetric. And so if you use that property, the symmetry of the stress tensor, this contraction between these two tensors, you can actually write it as the symmetric part of W contracted with sigma. And what is the symmetric part of W? Well, it's essentially 1/2 of grad W plus grad W transpose. So this whole thing contracted with sigma. And notice that this guy here resembles what?
Strain.
The strain. But it's not really the strain, right? It's because it's not operating on U, it's W, right? So what is it? No. I mean, notice that it's operating on W, which is our test function. So it's not really our physical strain, right? It's called, it's our virtual strain. And that is how we get into the same form as you all know, the principle of virtual work, where sigma, right, is contracted with our virtual strain. And this is the way it shows up. And the reason for that is indeed that I have used the property of the symmetry of the stress tensor so that I can write this grad W as the symmetric form of W, right? Symmetric gradient of W. Okay, so we take that out of the way so that you understand that there is this equivalence, right? Some people, I prefer to come from all of this weighted residual approach, and well, some people just state the principle of virtual work, right? And there are some subtleties. I like a little bit more the mathematical approach, but of course, when you talk about the principle of virtual work, you already have in mind the sort of functions that you're going to be dealing with: smooth enough, satisfy boundary conditions. These are the things that normally come to mind when thinking about the principle of virtual work. Okay, here, well, we look at it a bit more mathematical. We talk about subway spaces. That means that, yeah, well, the functions have to be smooth enough. They have to be square integrable. Okay. Okay, so then to finalize the expression, we're going to have on the left-hand side of the expression everything that we do not know, right, that depends on U and depends on W, and that is going to be part of the bilinear form, right? So what are those? Well, we have sigma contracted with the symmetric gradient of W, and then we have the part of the Robin boundary condition that we don't know. Is the integral over gamma H, and then we have W dotted with H operating on U. Remember that H is a tensor, and that is going to be equal to the integral over omega, and this term does not change. This term remains the same. We didn't even touch that term. And then there are two other terms that pop up. One is our Newman boundary condition. Let me just get some space here. So we have our Newman boundary condition, and then finally I have the other part of the Robin boundary condition, which is the part that we know. Remember that my U bar is something that we know the value, so we can actually use it, and it's going to modify the right-hand side. So everything that you have on this side of the expression is our bilinear form, and everything that we have on this side of the expression is our linear form. And so our final weak formulation in abstract form is going to be find U in that space of functions such that the bilinear form is equal to the linear form for all W's in that space. And again, keep in mind that this works because, well, we are assuming for simplicity that we have 0 essential boundary conditions being prescribed somewhere, if any, right? The moment that is no longer the case, we play the same trick as we saw earlier in the course, right? We define a linear variety where our U function is defined as the sum of two functions, one that satisfies the prescribed non-homogeneous boundary condition, and the other one that is the unknown part. And so we are, in the end, looking for the unknown part of the solution in that same space V0. Okay, the same trick we applied earlier. And well, we still have a few minutes, so let's write that more formally. Okay, so where might be the bilinear form of u w. Well, it's going to be equal to all of this. And my linear form yeah. And I will repeat what I said about boundary conditions, right? If we are dealing with non-homogeneous essential boundary conditions, we do the same trick. So we define the linear variety which, if you remember, is a translation of a space by a given quantity that satisfies a priori the boundary condition. So the linear variety is going to be v star is equal to some function u tilde plus v naught. Essentially, what this is saying, and it's not mathematically correct because here you are basically adding a space to a function, but you should read this as basically every single function in that space is being added to another function u tilde that satisfy a priori our boundary condition, such that the restriction of this u tilde at gamma u is our prescribed Dirichlet boundary condition. And so we are going to write our unknown u as the sum of two functions, v plus this u tilde. And now we are going to try to find v in the same set of functions as w. And that is how we define this Bubnov-Galerkin approach again, where we're taking both v and our test function from the same set of functions, okay? And so our weak form becomes find v, not u, in v naught, such that, well, the bilinear form of v comma w is equal to the linear form minus the bilinear form applied to u tilde w for all w in v naught. And as we know already, the fact that we know this guy u tilde, that is again the function a priori satisfy the boundary conditions, well, that is known. Eventually is going to modify the right hand side of the expression and change the force vector accordingly. Okay, we managed to do this in half an hour. We went fast, but again, you have it. You have the video, so at home you can play it one more time. Some people say that normally they have to play my videos at 2x because they are too slow. So this one maybe you're gonna play it at 1x because we went a bit fast. Any questions regarding this? We still have, yeah, we have 4 minutes. So notice it's exactly the same thing we did in heat conduction, right? Except that now we have to deal with a little subtlety, you know, just to try to figure out what this identity is. That was all we had to do in addition to the heat conduction problem. Everything else remained pretty much the same. We had to apply the divergence theorem as, again, a generalization of integration by parts to get that integral over the volume to be an integral over the boundary so that we can get our natural boundary conditions pop up in the formulation. Questions? You have a question?
I wanted to have a quick look at the vector fields.
Yeah.
Before we define the vector field V star.
Yeah?
Down.
The linear variety.
Yeah.
Yeah.
You're right. Before that, I thought that U itself is part of a different vector field, right? Because that's part of the vector field of V star. But I don't see that. I don't see that being defined up.
Defining U. You want to?
So basically, where you say it's a non-homogeneous essential boundary condition, we define a linear variety V star.
Yeah.
Comprises of U tilde plus V0, V naught.
Yeah.
Where basically we defined V naught previously as being a vector field where we.
V naught is this is a space of vector valued functions. So that's a space.
Sorry, that's a vector, but, and then basically you tilde is.
Yeah, it's a vector.
Is a vector.
That's why I said don't look at this expression as a mathematically correct, but you should think about this expression as a translation of a
Yeah.
space by a quantity that you know. It's basically you take every function in that space V naught,
Yeah.
right? And then you add something that you know, which is a function u tilde that satisfy your boundary conditions a priori, right? And that is a new function that is contained into this V star.
Yeah, but my question is,
Yeah.
now, if you look at the bottom sentence, you see that both vectors are part of the same vector field, but that must imply that U was not part of the same vector field as W previously.
Yeah.
I don't see that being defined anywhere else.
Yeah, so in the beginning,
Or is that, did you apply that indirectly?
look, in the beginning, in all this first derivation for the weak form, right? And all the way up to the way we are defining this expression,
Right.
so U belongs to V naught and W belongs to V naught as well, right? What we're saying there, this is correct as long as you have zero prescribed displacements.
Right.
This is correct because I'm taking U and W from the same space V naught.
Right.
And V naught was defined as the set of functions so that they satisfy zero prescribed boundary conditions, right? So, but this we do it for simplicity, and then we say, well, in the end, in the case that we have non-homogeneous, then we define the linear variety because that's the way we deal with this.
Right.
Yeah. Okay, guys, 10:30 exactly. So we finish here. Tomorrow you meet Martin again, and this afternoon you have the project. Okay, so you can start working on it.